Hello everyone. In this video I will discuss about Z transform. Okay, Z transform is used to convert time domain signal to complex frequency domain signal. It's same as Laplace transform. Laplace transform also used to convert from time domain to frequency domain. However, Z transform is used to convert a discrete version of time domain. Laplace transform convert continuous time domain. Okay, let's say we have our time domain here, time domain signal. Okay, we have two types of time domain signal. First, let's say continuous time, and also we have discrete time. Let's say our continuous time like this. Continuous signal, we have t time domain, ft, function of t. Let's say our graph continuous like this, and then we want to convert from time domain, we want to convert to frequency domain. Okay, this is time domain, so this part is frequency domain. Okay, we know that to convert from time domain to frequency domain, we can use Fourier transform or Laplace transform, and also the latest one is we can use Z transform. Okay, this type of transform is used to convert from time domain to frequency domain signal. Okay, Fourier transform, we can, to convert from continuous time, we can use Fourier transform. Continuous time, Fourier transform. Okay, it will convert from continuous time to frequency domain. This one is frequency domain. So omega for frequency, this is magnitude. So it will convert from this type of signal, time signal, it will convert to frequency domain. Let's say like this, omega 1 minus omega 1. Okay, this one we use continuous time Fourier transform. Okay, we also can use Laplace transform. If we use Laplace transform, our time domain will be complex frequency domain. Like this is magnitude, this is imaginary part, real part, this magnitude. Okay, this is we call S-plane. So our output will be our frequency domain will be like this. Okay, this is our frequency domain. For complex frequency domain, we have imaginary, we have real. S-plane. This one is we use Laplace transform. Okay, next is second type of time domain signal is discrete time. Let's say this is our discrete time, xn, this is n. Okay, means that discrete time. For example, this is the example. Okay, discrete time. So we have n is for integer. So we want to convert from time domain to frequency domain. We can use Fourier transform. This is we call time domain Fourier transform. So it will convert from time to frequency. Discrete time. This is discrete time. Frequency domain, omega, magnitude. So for example like this. Okay, omega 1 minus omega 1. And also we can use Z transform. Okay, this is we want to convert from time domain to frequency domain. We can use Z transform to convert from time domain to complex frequency domain. So we have complex planes, imaginary, and also real part. This is magnitude. So our response will be, for example, this one. Okay, this one is complex frequency domain. Okay, we use Laplace transform. Actually, it is same as Z transform. Alright, so we can see that Z transform as a discrete version of Laplace transform. Okay, it is to convert from time domain to complex frequency domain. Okay, this one is discrete time domain. Okay, convert to frequency domain, same as Laplace transform. Okay, in Laplace transform we use S, or variable is S, equal to sigma plus j omega. Okay, however in Z transform the variable is Z. Okay, real Z and imaginary Z. In Laplace transform, this is complex. Okay, in Laplace, this is complex plane of Laplace transform. So this is called S-plane. In Z transform, this plane, this is complex domain of Z transform. This is we call Z-plane. Imaginary of Z and real of Z. Okay, this for Laplace transform. Imaginary of S is real of S. Okay, real of S is sigma. Imaginary of S is j omega. This is general equation for Z transform. Okay, Xz equal to summation from n equal to minus infinity to infinity, Sn sec minus n. Okay, let's say we have our discrete time signal is as Sn, so we want to transform using that transform. Okay, we can use this equation equal to Xz, capital letter of Z for Z transform is equal to summation of Z, summation from n equal to minus infinity up to until to infinity. Sn is we just substitute our discrete time signal that we want to calculate. So this, they say this is our discrete time signal. We substitute here. This is our equation. We substitute the equation same as Laplace transform. Laplace transform we have ft. For Z transform we use xn. So we substitute our equation here. That our signal we want to calculate. Then we times z. That one is for Z transform. This is power of minus n. N is integer. Okay. Z is a complex variable. Z is a complex variable. Complex variables is Z equal to R E J omega. Okay, this is in polar form. R E J omega is polar form. Polar form for complex variable. This is Z for complex variable. R E J omega is in polar form. Okay, R is a magnitude. R is a magnitude of Z. So magnitude of Z. Magnitude of Z. Okay. Okay. This one is n equal to infinity for bidirectional. So we also can have a unidirectional. For unidirectional, n equal to 0. N equal to infinity minus infinity. So bidirectional. N equal to 0. So we start from 0 is for unidirectional. If you notice here, Z is equal to R E J omega. If we replace R with 1, or unity, so this will become E minus j omega n. Okay, so this equation, if we replace with this equation, and overall equation will become our discrete time Fourier transform. Okay, so we can say that Z transform also is a generalized of discrete time Fourier transform. Generalized discrete time Fourier transform. So we can use this equation for discrete time Fourier transform when R is unity. So our magnitude is unity. Okay. From complex frequency domain, we can see that they have a magnitude axis, imaginary axis, and also real axis. Okay, this axis we can zoom here. So we zoom this, we call Z plane here, just imaginary and real. So we have imaginary, horizontal is imaginary. So vertical axis is imaginary, and also horizontal is our real part. This part is horizontal, this one is vertical, become a vertical. We rearrange it, become vertical. We call that one is imaginary axis, and this one is real axis. So from this equation, we know that Z is equal to R E j omega, where R is a magnitude of Z. So this is our R. From this graph, this is R. This is the magnitude of Z, R, and this is the location of Z. Okay, omega is angle. So angle omega. So when omega equal to 0, our Z will be here. Omega equal to 0, our Z will be here. When omega equal to pi, our Z will be here. Omega equal to pi or minus pi. Okay, this one is our the location of Z, so it will lies around this circle. Okay, depend on omega. When omega equal to 0 or to pi, you will here. This one is pi and minus pi. Okay, this we call Z plane. Same as Laplace transform. Laplace transform, we have S plane. From this equation, we can get the roots. Z of poles. We can get the 0 of poles, 0 and poles. Okay, let's say we get poles. So this pole is the axis in the Z plane. For example, let's say we have a pole here. So in Z plane is in here. In frequency domain, in complex frequency domain plane, it can be here. Let's say, for example, here. So our graph will be like this. Or we have another 0. Let's say we have another pole in a pole here. So maybe our graph here. Okay. Or we also can have poles on the unit circle, our unity circle here, or here, or here, or here. So if our 0 is our pole is on this unit circle, so that's mean in the circle, that's mean our graph will be on the imaginary axis, like this. You see on this one. So this one is during imaginary axis, that is on the circle. Yeah, okay. That's all. Thank you. Bye bye.